Hi, everybody. So I want to take you through a proof of the fundamental theorem of arithmetic, which says that every natural number has a product. It can be written as a product of prime numbers, and there's really, up to rearranging the factors, only one way to do that. This was first proved by Gauss in the 19th century, and it illustrates a lot of the techniques of proof that we've been using, and it's a fairly significant result, so it's worth the effort. I just want to emphasize that I'm not going to make a big deal about the section of the book that talks about proof by minimal counterexample, although I will use that technique in this proof. And so you should be sure to read that section and look at the example. But there may not be a specific lecture about it. Okay, so let's look at the fundamental theorem of arithmetic and sneak up on it step by step. So we need to prove a preliminary result before we can deal with the fundamental theorem of arithmetic. And in order to prove that result, we're going to rely on something that we showed back in the chapter 7, I think, which is what I called Euclid's algorithm. And it says that if you have two natural numbers, a and b, then there are integers k and l, so that the greatest common divisor of a and b can be written as ak plus bl. So we spent a lot of time working through the proof of this fact, and so I'm going to use it now in the proof of the fundamental theorem. And the first step towards that proof is to show that prime numbers behave kind of the way you think they do. That is to say that if you have a product of a bunch of numbers and you have a prime number, let's say 7, and 7 divides into this product of numbers, then it has to divide into just one of them. Somehow the idea is that if that wasn't the case, then part of the 7 would have to go into one of the numbers, part of the 7 would have to go into the other, but since 7 is prime, you can't split it up. And now we're going to try to make that argument rigorous. So the proposition that we're going to try to show is that suppose we have at least two integers, and we have a prime number p, and if the prime divides the product of all those numbers, then it divides at least one of them. So remember what this is saying, what divides means. This means that if a1, the product of a1 up to an is pk for some integer k, then one of the ai's is pk prime for some k prime. And the example is, if you look at a number like 7, and you look at 7, and let's say the numbers that it divides are 21 times 16, the only way 7 can divide 21 times 16 is if it divides either 21 or 16. And of course, in this case, it does. 7 divides 21. So we're going to prove this by induction. We're going to start with the case 2. So this is a proof by induction. And we have to start at 2 because if there's just one number there, there's nothing to be said. We don't have a product. So we suppose we need to first show the first case. We must show that if p divides a product of two numbers, then p divides one or the other. And this may seem obvious, but actually to do this correctly, you need to use Euclid's algorithm. And the way we're going to do it is we're going to start with p and a1, and we're going to notice that the greatest common divisor, we're going to look at the greatest common divisor of p and a1. And there are two possibilities. Either it's equal to, it has to be a divisor of p. So either GCD of PA1 is p, or GCD of PA1 is 1. Well, if it's p, we're done. That means that P divides A1, so we are done, because we needed to show that P divides A1 or P divides A2. This is a nice example. If you're trying to prove an OR statement, then in the first case, we're done. But of course, the other possibility is that if GCD of P and A1 is 1, then P doesn't divide A1. But we can use Euclid's algorithm to find K and L so that 1, which is the GCD of A and P1, A1 and P, and now we can multiply this equation by A2. And notice that on the right-hand side, A1, A2, since P divides A1, A1, A2, A1, A2 is P times some S, and therefore A2 is P A2K plus PSL, which is P times A2K plus SL, so P divides A2. So what we've shown here is that either P divides A1, or we can use Euclid's algorithm and conclude that P divides A2. And that's our first step in our induction. Now suppose that we have the case where if P divides n numbers, then P divides AI for some I. That's our inductive hypothesis. It's the P of n statement. And we want to show that if P divides A1 up to AN times AN plus 1, then P divides AI for some I. And here, the trick, the inductive step, is to write, but P divides A1 up to AN times AN plus 1. And that's just two numbers. Here's the first number, and here's the second number. So by the first case, either P divides AN plus 1, or P divides A1 times AN. And then by the inductive hypothesis, P divides AI for some I. And this finishes the proof, because we've shown that P, in either case, P divides one of the numbers A1 up to AN plus 1. So it's kind of a nice trick. You take the n plus 1 numbers and you convert them into two numbers, and then from the two numbers you go back to n numbers and you get what you need. So that probably requires some thought, but that's the idea. Now we have to go on to the next step, and we're going to take on the theorem itself, which says that any integer n has a unique prime factorization, meaning that it can be written as a product of prime numbers, and any two such products differ only up to the order of the factors. So there's really two parts to this theorem. First, that you have a prime factorization, and second, that it's unique. So we're going to take the first part first, that every integer has a prime factorization, and we're going to do this by strong induction. So here's the proof of the first part. I should maybe say, not integer. Let's say it's an integer n bigger than 1. So it's every natural number. Otherwise, we have to worry about signs, and that's just confusing. So take a natural number. We're going to do this by induction. So let's start with n equals 2. Is prime. so it has a prime factorization. Namely 2. Now suppose n, suppose that all integers, this is strong induction, so all integers from 2 up to n have prime factorizations. And let's consider n plus 1. Well, there are two cases. Either it's prime, in which case it certainly has a prime factorization, namely itself. Or it's composite, so it's equal to a times b, where a and b are at least 2 and less than or equal to n. In other words, either it's prime, in which case it has a prime factorization, or it can be factored into 2 smaller numbers. And this might remind you of the proof by strong induction involving the trees. What we did is we split the number into 2 smaller numbers. By the strong induction hypothesis, A is a product of primes, and B is a product of primes. And therefore, n plus 1, which is P1 up to PR times Q1 up to QS, is 2. It's also a product of primes. So if you remember in the proof involving trees, we took a tree, we picked an edge and pulled it out, then we had 2 parts. Those each satisfied the condition, and then we put them back together again. That's exactly what we did here. We took n plus 1. If it wasn't prime, we factored it into 2 parts. Each of those parts has the property that we're interested in, and then we put them back together. Okay, so we're almost done. We just need to satisfy the uniqueness condition. That is to say, we need to show that there's only one way up to reordering the factors to write an integer as a product of primes. And here's where we use the technique of minimal counterexample. So remember what we do is we suppose that there is some integer which has 2 different prime factorizations. And using the idea behind minimal counterexample, we pick the smallest such integer. So we know that n can be written P1 up to P sub r, and it can also be written Q1 up to Q sub s, where all these Pi and Qj are prime. And our assumption is that that these are different, and that any smaller number, they're not, if you had 2 factorizations, they would be the same. So notice that P1 divides n, right? It's the first prime here. And so P1 divides Q1 up to Qs. Now remember what our very first lemma that we proved on our way to this point was. We said that if you have a prime number that divides a product, it has to divide at least one of the terms in the product. Therefore, there is some Qj, j between 1 and s, so that P1 divides Qj. That was our earlier result. But these are both primes. And if they're both primes and one divides the other, they have to be equal. So P1, the first prime on the left, also occurs somewhere among the Q's on the right. So let's divide it out. Let's let N1 be N divided by P1, and it's equal to P2 dot 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 up to P sub R, but it's also equal to Q1, Qj minus 1, Qj plus 1 up to Qs, where I've omitted Qj, which is the one that we canceled from both sides. Now, N1 is smaller than N, so it has a unique factorization. Remember, N was the smallest number which didn't have a unique factorization. And that means that Q1, Q2, Qj, Qj plus 1 up to Qs has to equal. I mean, I shouldn't use set braces here because some of these could be the same. They're not all different. But this collection of prime numbers has to be the same collection as P2 up to PR. But then that means that N, so N1 is equal to P2 up to PR. So N, which is equal to P1, P2 up to PR, is equal to Qj times Q1, Qj, Qj, J minus 1, J plus 1, Qs. And these are the same. And so we've actually shown that since this is actually equal to P1, and this is actually equal to P1 up to PR, we've actually shown, P2, I'm sorry, up to PR, we've actually shown that what we thought were two different factorizations are actually the same. And this is a contradiction. Remember, N was supposed to be the smallest number which didn't have a unique factorization, but now we've shown that in fact it does have a unique factorization. So this is a contradiction of the assumption that N is the minimal natural number that doesn't have a unique factorization. And so we conclude all natural numbers have a unique factorization. And that's the fundamental theorem of arithmetic. Just as a side remark, you might ask yourself how many fundamental theorems you know. There's a fundamental theorem of calculus. You probably learned that. There's a fundamental theorem of algebra. You probably learned that. Maybe. But do you know any other fundamental theorems? Anyway, that wraps up this discussion.